Let's talk about feature importances in random forest. Previously with the decision trees, we saw that we have these two major problems. Our first problem was about the dependency on the tree structure, and our second problem was about these correlated variables. When we use a random forest model, we can solve both of these problems. For the first problem, in our random forest, we will have multiple trees, and we will have this averaging effect. And with that, we won't really depend on this single tree structure. For the second problem, in our random forest, we will just consider this random subset of the features in our trees, and with that, we cannot really focus on this single feature and just use that exclusively. And as you see, we can solve both of these problems if we just switch to a random forest model. How about the formula? The formula also stays the same. We will just calculate this feature importance over all the trees, then we will take the average of them. Let's also go back to our previous exercise. In that exercise, we fit a simple decision tree on this MNIST data set, then we looked at these feature importances. This time we will go ahead and use a random forest, and we will try to see what happens to our feature importances. Here our random forest gave us 97% accuracy on the test set, and overall when we look at this feature importance figure here, it make more sense to us. We see a smooth result here, we don't see a bunch of dots, and overall things started to make more sense. For example, over here this middle part looks like the most important part, and it makes sense because when you consider digits here, when you consider a 0 here, for example, there's nothing in between, versus 1 here, maybe a 2 here, you see that this middle part is kind of important to us. Similarly, we have this top part, bottom part, and this diagonals here, which kind of looks like important. And again, this makes sense because our digits actually may be overlapping mostly in these areas. So it kind of looks important to our model. And overall, this is a vastly improved result compared to what we had before. And this is the second part of our notebook, so you can go back and also run this to get the same visualization. Okay, so far we saw that if we switch to random forest, we improve our results. But even if we do that, we still have some issues. The first issue is about the continuous variables, because they are often considered more important than the discrete variables. Similarly, for the discrete variables, the ones with the more classes are usually considered more important than the ones with less classes. And again, this all boils down to the fact that if you have more choices to make, or if you have a more chance to select something from a larger pool, we usually end up choosing from that, because we have a lot of things to try. And if you want to dive deeper, there is this paper and there is this blog post that explains this in a greater detail. And we have a consequence here as well. For example, if you make an experiment and create a dummy column with just random continuous values in them, you may see that that column actually picks up a lot of future importance because of this phenomena here. Similarly, collinearity is a problem. For example, if you have some correlated columns, in this case, they will also share this future importance. And these are the things that you may expect to see from your future importance calculations. Okay, we have come to the last topic for today, permutation importance. So far, we've used this entropy, Gini, or mean squared error as some type of feature importance. But there are also some different approaches. For example, this is one of them, permutation importance. With this one, we will do a different thing. We will first fit our random forest model. Then we will look at this out of the back or validation error to see the performance of the model. Then we will take this trained model and we will go to our data set and we will shuffle one of the features. We will take that column, we will shuffle it. Then we will take that data points. Again, these data points are from our validation samples. And then we will look at the accuracy on these shuffled features. And you can think of it as, for example, if that feature is not important, maybe it's not even used in our trees. In this case, this wouldn't change anything, right? We should get the same accuracy. But on the other hand, if this feature was important and it was used a lot, then in this case, we probably do a bad job in this accuracy. So that's the main intuition behind this. So we look at these accuracy scores, and if we see a large decrease, it means that that feature was important. If you don't see a large decrease in accuracy after this experiment, it tells us that this feature is not that important. So this is an intuitive, nice idea about feature importance. One problem with this approach is that it is quite slow. So when you run this, you should be quite patient to see your results. So we actually did that. We have a notebook for this. So we created this 10 shuffles for efficiency because it's quite slow. And then we created these feature importances from those. Overall, actually, this looks really similar to what we had before. So we don't see too much of a different result here. And we had this great discussion about the benefits of this here. But one thing that I want to point out is that this is extremely inefficient. This picture that you see here, which is almost the same as our previous result, took almost an hour, actually. So be careful about that. And we have this notebook here if you also want to reproduce this picture here.